Hello friends, welcome back to Scientific Blunders, where you learn the don'ts first. So today we'll be continuing our series on probability, and here's the problem we have. Let x be a random variable with a uniform distribution from 0 to 1. Find the probability that x takes the value 0.5. Right, so let's just quickly graph the distribution of x that we have. So the x-axis is the value that the random variable takes, and the y-axis, it's the probability density, right? And so this is a standard uniform distribution from 0 to 1, which means the probability density would be a constant value of 1 everywhere, so that the area under the curve equals 1 by definition of a probability distribution. Okay, perfect. So now we want to find the probability that x takes the value 0.5. Right, so what is the probability that x takes the value? I can do a better job with that. So what is the probability that x takes the value 0.5? Right, so in general, for a continuous distribution, we know that the probability that x takes a range of values between a and b is equal to the integral of the curve between those 2 points. So it's the integral from a to b of the probability density of the distribution. So let's just call that f of x. Let's say that function is f of x. So it's the integral from a to b of f of x dx. So this is by definition, right? And now we want to find the probability that x takes one particular value, not a range of values, but a single value. And so in our case, another way of saying that would be the probability that x lies between 0.5 and 0.5. So if x has to lie between 0.5 and 0.5, it has to equal 0.5. In other words, so this would be the integral. So a is 0.5 and b is 0.5. And f of x is just 1, right? For all values of x between 0 and 1. So f of x is just going to be 1, and then we have dx. And if you were to compute this integral, because the limits are the same, essentially it's the area between, there is no area really, because the limits are the same. So this integral would be 0, right? Let me just scroll down a little bit. So in other words, we are saying, or we have calculated, the probability of x taking the value 0.5 equals 0. Isn't this interesting? And from our conventional understanding of probability, if the probability of something is 0, it's an impossible outcome. And if the probability is 1, it's definitely going to happen. So it's like a definite outcome. And if the probability lies between 0 and 1, it's uncertain, which is typically how most random variables tend to behave. And now we have just basically, based on this logic of ours, we have reached the conclusion that the probability of x equaling 0.5 is 0, which means x can never equal the value 0.5, right? Isn't that what our understanding, uncertain, yeah. So does that mean that this is actually impossible from our conventional understanding of probability? I'm sure all of you have messed around with random function generators, either in a programming language or maybe even on Excel. And you can try this on Excel really quick. So choose any cell on Excel, any cell, and just type in these words. rand and just parentheses, and this will generate a random number between 0 and 1 for you. So essentially what this function on Excel does is it draws numbers based on this particular uniform distribution. So it will basically draw a number from this distribution so that every number is equally likely. So the probability density is going to be the same. And if you run this, you can keep pressing F9, and then it will keep generating new random numbers each time. So maybe the first time it generates 0.43, and the second time it generates 0.72, the third time it generates 0.68, and maybe the fourth time it generates 0.5 exactly, which would be surprising, but it is possible, right? And excuse me, what is this? What exactly is going on here? Because we just concluded that x taking the value 0.5 is an impossible outcome, and yet when we generate random numbers drawn from this distribution, all of these outcomes seem to be possible. And unfortunately I'm not able to share my screen on Excel right now, but I really encourage you to try this out, and you will notice that every outcome on this in this particular range is a possible outcome even though the probability is 0. So why is that? What exactly is going on here? I encourage you to pause the video and think about this, because this is really very interesting. So assuming you have paused the video and are back with hopefully some more clarity on this, let me just create some space, or let me actually just go down. The way I like to think about it, and by no means is this a very formal mathematical proof. I'm sure a rigorous proof for this would have complicated Greek symbols and a lot more abstract math. But the way I like to think about it is that let's just quickly redraw the distribution that we had. So this is x, this is the probability density, and we like to call that f of x, and this is 1 for the range of values 0 to 1, right? So the way I like to think about it is that suppose we want to calculate the probability that x takes the value 0.5, right? So how many real numbers are there between 0 and 1? How many real numbers are there between 0 and 1? There are infinitely many real numbers, and of those infinitely many real numbers, all of them have equal probabilities, right? So what is, of those infinitely many real numbers, we are interested in one particular real number, right? We are interested in exactly one real number, and we want to compute its probability. So basically you have an infinite number of real numbers to choose from, of which you're interested in exactly one real number. And so this is a fair definition of probability, right? You have infinitely many options to choose from, and you're interested in one of them. What is the probability that you pick that one option? Well, it's 1 over infinite, or 1 over infinity, which equals 0, right? And that is, based on my understanding, that is basically what this calculation of the probability gives us. It tells us that of the infinitely many real numbers between 0 and 1, we want to choose exactly one, and so that will tend to 0, right? Which is basically what we have shown here. Whereas if I'm, let's say, interested in the probability that x takes the values anywhere between 0.5 and 1, right? So let's do this two ways. One is based on the more formal definition. So that would be the integral from 0.5 to 1 of f of x dx, and f of x is 1, right? It's just a 1 everywhere, so dx. And if you were to perform this integral, you would get half. So it's basically this. Let me use a different color for that. It's basically this area that gives us the probability that x takes the values 0.5 to 1, and that equals half just by symmetry, and or from performing this integral. Alright, so what, this is definitely interesting, but why was this 0 and why is this half all of a sudden? So again, the way that I like to think about this is that now you have, the denominator stays the same. You have infinitely many real numbers to choose from, right? There are infinitely many real numbers between 0 and 1, of which you want to choose numbers that lie from 0.5 to 1, right? So how many real numbers are there between 0.5 and 1? Well, there are also infinitely many real numbers, correct? And now infinity over infinity is indeterminate. So it could be 0, it could be infinity, it could be undefined, or it could be a real number. We don't know. But there is a possibility that this could equal a real number. And again, the way that I like to think about it is, let's consider the limit. Let me use a different variable. A tends to infinity of x over 2x. Oh, I'm sorry, I just changed the variable. A over 2a. So as a gets larger and larger, what is the limit of a over 2a? Alright, so I mean, this is fairly simple, but a is going to get larger and larger, so a is going to tend to infinity. 2a is going to get larger and larger, so 2a is also going to tend to infinity. But we see that somehow the ratio of a to 2a is always going to be 1/2, right? So no matter how large a gets, we are always considering the ratio a over 2a, and so that is going to tend to half. So by a very similar logic, here in the numerator we have the number of numbers. So this is the number of numbers from 0.5 to 1, and this is the number of numbers from 0 to 1. So both of them are infinite, but when we consider the ratio, it magically equals half, which is why we have a probability of 1/2 here. Whereas in the first case, when we considered the probability of x taking the value just exactly 0.5, that was just one particular number out of infinitely many numbers, and so that equals 0, right? So I hope you found this interesting, because this is always, it's actually funny because there are other ways to think about this. So let's say there's a dartboard, right? And you want to, let's say you somehow, the way you modeled, so there's obviously the center of the there's obviously the center of the dartboard, which is called the bullseye, I think. So the way you would model this, as a probability distribution, let's say this had a constant probability density everywhere, right? So the probability density, let's not get too much into the details, but it would be 1 over the area of the board. Now, what is the probability that you hit exactly the bullseye? Well, the probability, there are infinitely many points on the board, out of which you want one point exactly. And so that, by the same logic that we saw here, that is going to equal 1 point over infinitely many points, and that's going to be 0. And yet, that's a possible outcome, right? And so this is I think this is an important concept that has applications in several places, and therefore it's very important to get a good interpretation of what 0 probability means for a continuous distribution. And so before I close our session for today, I just want to give you the key takeaway from all the things that we did today. It's that 0 probability does not, and this is in the context of a continuous distribution, 0 probability does not mean that it's impossible, right? And that, my friends, is the key takeaway from today's video. See you guys soon.